Hello, disclosure. My name is Jan Shortashvili, and I am here from Arizona State University, actually from my home, of course, to talk to you about cyber autonomy and my journey investigating cyber autonomy and then understanding how to take cyber autonomy from theory to practice. Of course, this journey is fraught with peril, and I'll mostly have as takeaways the peril that we've run into in this journey. Hopefully, you will find this an interesting view into kind of the other side of the fence. Disclosure is very much an industry-focused venue, and I'm an academic, right? In a past life, in my graduate school career, I participated in cybersecurity competitions in the form of Capture the Flag, an interest which eventually led me into the DARPA Cyber Grand challenge, which was the first fully automated cybersecurity competition in history. I'll talk about that today, and I'll talk about the technology that came out of it. So let's get started. Let's take a step back and understand why we needed something like the Cyber Grand Challenge, why we needed an automated cybersecurity competition, or why we need academics in cybersecurity anyways, right? The simple truth is we're not keeping up with security. On screen here is a graph of the number of CVEs per year, excluding reserved CVEs. These are just the public ones. And you can see this interesting trend starting in the early 2000s when no one really cared about security. Security was, there were worms every other week and so forth. And then through the mid 2000s and up until the mid 2010s, when there was more emphasis on security. Security was definitely an important thing, but there were still kind of a relatively low amount of vulnerabilities that were being discovered. And suddenly in 2017, 2018, 2019, vulnerabilities skyrocketed. So there's a number of ways of looking at this graph, right? One way, a pessimistic way, might be, holy crap, look at all of these vulnerabilities, right? That's pretty bad news. An optimistic way might be, hey, we're getting better and better at finding these vulnerabilities, right? So, of course, we'll have more. Interestingly, it's interesting to take some other data, overlay it with this. So let's look at, for example, the number of lines of code in the Linux kernel scaled to a scale where in 2016, the lines of code on whatever largely reduced scale matches up with the number of CVEs in 2006, right? The Linux kernel has grown. It has grown at a shocking pace, but a continuous one. And if we look at the increase in the code size and presumably the code complexity of the Linux kernel, it has outpaced the amount of bugs that we as a society are finding and reporting and fixing. This seems to imply that there are a lot of bugs in the Linux kernel that have probably made it in there and are just not being found. That's one potential observation. Another potential view is Linux kernel got secure and there are just no bugs to find, and the bugs per size of code has decreased over time. But there's no evidence to suggest that. What's worse, it's not just that the Linux kernel is growing, the amount of projects out there is skyrocketing. Over this course of relatively flat amount of vulnerabilities that we've been finding over the years, from 2017 up through, right now in 2020, we're on track to hit roughly the same level. The amount of repos on GitHub, repositories on GitHub, has more or less doubled and is still growing, right? So there's more software out there. The software is bigger, but we're still finding the same amount of vulnerabilities. This implies to me that we have hit some sort of cap in the capacity of the human talent to find and fix these vulnerabilities. And that's a problem. So of course, looking back, quite a while, academics have been thinking about this because we were very wise as academics. So even back 70 years ago, Alan Turing started thinking about how do you verify that a program is safe, or that a program is correct. Now, let's say we'll at least take that the program is secure, right? If you have a benign bug that the program doesn't work properly, but at least no one gets hacked and your company doesn't show up in a news report about a giant disclosure, okay, we'll take it, right? Alan Turing in 1949 wrote this awesome paper, and when I found this paper, it's the first written work that I've seen, the earliest, where the author talks about, okay, how can we verify that a program is correct / secure / whatever the property you're trying to verify? And Turing writes in this very interesting way that the verifier does this and takes these steps and so forth. Now I'm reading this coming from the perspective of an academic in modern times. I'm thinking, wow, he's way ahead of his time. He's talking about, programs verifying programs. I thought that we hadn't started thinking about this until much later, and it turns out we hadn't. What Turing meant was a human that was verifying a program. But, with the goal of understanding, is the program secure? Turing is interested, is this program secure? Well, it's very easy to answer the question. The software available to Turing was very few and far between, right? There wasn't a lot of software in the world back then. Now we know through experience. You can give me a piece of code and you can ask me, is this program secure? I have a perfect technique. I've solved this problem. I'll tell you no, it's not. You might laugh at this, but in my past experiences, I have won points at cybersecurity competitions by giving this answer. A poorly worded question where a complex web server was given, and the question said, is there a memory corruption vulnerability in this web server? Of course. I said yes, and that was correct. Right? They didn't ask for the memory corruption vulnerabilities. They didn't ask for a test case to trigger it or any sort of localizing information, which made this a trivial problem. So academics have since wised up a little bit in this regard. So I'm going to run you through a couple of techniques that had been developed in the run-up to the Cyber Grand Challenge, which we applied as a frame for talking about issues in the real world. First, we need to do some background learning. Background learning specifically of cybersecurity concepts. There's a simple program. It's written in some sort of a Python-like pseudocode. Of course, all of the techniques I'll talk about, and as I'll mention later, they work on binary code directly, compiled, no source code, etc. But let's take a look at what this program looks like. Right, this program is made up of a bunch of what is called basic blocks. A basic block is a set of code that always runs together. Right, so this input of the username, followed by a check of the username against a hard-coded credential of service. This always runs together, and then control flow will go into one of two branches. Either the if is true or the if is false. Those are two more basic blocks, so let's follow the true case. There's another chunk of code that always runs together, another basic block, and that leads to two more basic blocks, one of which we have a bug that crashes. So if you put in a hard-coded username of service and a command code of 7, the program will crash. That's a bug that we would like to discover and report to the user. If you don't, and then it exits, of course. If you don't put in a hard-coded username, it'll try to authenticate you with a PIN, and then either succeed or fail and go back to the exit. So altogether, all of these basic blocks create what is called a control flow graph. A control flow graph of a program is the basic blocks of the program arranged with the different control flow as edges and the code as blocks. Nice and simple. So now we can start talking about some awesome analysis techniques that we've come up with. I'm not saying myself and my research group, but we as a society have come up with to identify vulnerabilities as code. Now I'll put kind of best foot forward and go with the most effective one first. This most effective one is fuzzing. It actually is a very, very old technique. Back in the 1950s, when programming on punch cards, programmers would take discarded punch cards from the trash and use them as inputs to test the resilience of their routines to unexpected data. This was formalized scientifically in a software engineering conference, academically, in 1981. And it had continued to evolve gradually until this massive jump in 2016 by Mikhail Zalewski, who created the first, let's say, modern fuzzer called American Fuzzy Lab. So let's talk about how this works, right? We have our program, our control flow graph, and then we have what is called a test case corpus. So a fuzzer starts out by sending random data or sending data that is some given inputs. You can initialize your corpus with some test cases, but let's say we start out with this initialized corpus of a username ASDF and a passcode of 1111, right? Of course, the fuzzer will execute the program with this data as input and will monitor the execution to understand how the program runs given this input, specifically what parts of the program execute. And it tracks this. And in this case, we give a username that is not service and a passcode that is less than 10,000, and so it's an invalid passcode. And so we triggered these 1, 2, 3, 4, 5 basic blocks in the code. And then the fuzzer starts making random mutations. There's a number of mutations that it goes through, but let's just say start with random bit flips. So the fuzzer might flip a bunch of bits in the input and start trying more and more different variations. And eventually, one of these variations bites and ends up triggering what is a correct or passcode, or a valid at least passcode. So it triggers an additional basic block and then says, aha! Now I have found a way to trigger new code, so I'm going to mutate that test case instead. And then it mutates that test case and keeps working for a while. It executes what is called a genetic algorithm, where it basically it'll take test cases, it'll swap bytes between them, swap parts, combine them, and keep the ones that trigger new, previously unseen code as seeds for the next generation, like a genetic algorithm. Fuzzers have problems in that they are very dumb. They're extremely effective. Don't get me wrong, this is the single most effective tool that we have to identify concrete vulnerabilities in software. But they are they have their problems. The basic concept presented by AFL, and of course, since then we have had 5 more years of research, but the underlying problem still exists. But the basic fuzzing approach will fail, will likely never actually find this check here, never figure out how to generate an input that will drive a program down that path, because it's dumb. All it does is mutate inputs. It's extremely effective, but dumb. And in order to randomly generate the word service, you have to get a whole hell of a lot of bits correct that you likely never will, and so you will keep exploring this part of the program that you've explored. Now, of course, now we have techniques to resolve simple string comparisons like this, but these comparisons can be arbitrarily complex, and the problem still stands in general. All right, So we still have an unexplored part of the program. How do we how do we create test cases that can reach it and can discover this crash? We can turn to something called dynamic symbolic execution. It's a way to mathematically model the execution of a program that was originally proposed in the 70s, in the mid 70s. So a lot of these techniques, as you're starting to see, have very old roots. Dynamic symbolic execution has this idea of emulating execution of a program, but instead of tracking bits, you track mathematical concepts. So let's take a look. All right, we have our program, our control flow graph, and now instead of test case corpus, we track mathematical constraints. Let me show you what this looks like, right? Let's say we're emulating the program from the beginning. We have a username that is given as an input, so we have a constraint. Of course, it's not much of a constraint, but a username is a variable that can be equal to anything at this point, right? And then an interesting thing happens. We hit this if statement, and we split the constraints into two sets. And in one set, we have username being equal to service, and in the other set, we have username not equal to service, right? So now, by splitting this into two sets, now we can easily, trivially reason about both cases. It is very easy to mathematically solve this equation, right? So let's move on. Then, of course, we go into this command code equals A2I and passcode into A2I, and this is where we run into theoretical problems that plague this technique, which is crazy. A2I is a function that takes, if you've written a lot of C, it takes a string representing a number, like the bytes, 1, 2, 3, 4, and it returns an integer with the value 1, 2, 3, 4. Right? A2I works as follows. We start with the string, which can be anything, right? Because again, remember, this input returns some unbounded variable, right? So it can be anything. And then we do something along these lines. We have a loop where at every iteration of the loop, we check, okay, is this character 0, 1, 2? I mean, this is a very trivial or very naive way of creating A2I, but the interesting thing about analyzing code instead of writing it is you don't get to choose how the authors of the code wrote it. You have to analyze it. So we will, and I have seen this type of code in my as an input into my analysis engine. We have to be able to handle it. So take a look at how this trivial A2I starts executing, right? So we hit the first set of if statements. Of course, this is a disaster because it splits our analysis state into 10 different parts. 11 different parts actually. One where it is the input is a 0, one where the first byte of the input is a 0, one where the first byte of the input is a 1, one where the first byte of the input is a 2, all the way to where the first byte of the input is not a digit. Pretty bad already. Already we took one step through A2I, and we now have to track 10 steps. 10 different analysis states, 10 different sets of constraints. Well, the problem is, what about the next step into A2I? Each of these will then split into 10 more, and we have an exponential explosion. This is called a path explosion that we have no choice eventually but to start throwing out paths more or less at random, right? How do you choose which path to go down to actually keep in your analysis engine? Because physical constraints and the lifetime of the universe make it impossible for you to analyze all of these states. Bad news. All right. Because of this, we have to make certain sacrifices and just keep a couple of specific paths through the code and end up with something that is not so nice, really something that does not still, in our case, find our crashing locations, right? That misses some code. there have been some techniques that try to get around this. Some researchers have created very interesting path merging instead of path reduction techniques. Actually, if you notice, this was published in the same conference as one of our original fuzzing papers that I mentioned that was published in the 80s. So there's a very long-running conference that is responsible for a lot of the academic work in this field. So these researchers created a technique that is basically a very smart way to merge paths rather than reduce paths. So in this case, we might be able to merge these paths into different constraint sets representing strings of different length. But these techniques have other significant problems in that they inject a lot of complexity into other parts of the analysis. And in our experience, don't really solve the problem in general, right? So I'll talk about a technique that we created for the Cyber Grand Challenge. We made the observation that fuzzing misses some parts of code, symbolic execution misses some other parts of code, but there is an interesting effect that if you overlay the two, you'll get much higher code coverage. And so we say, okay, what happens if you create a technique that can really use both fuzzing and symbolic execution? The result was Driller. I am one of the people in that et al. Excuse me. We published Driller in 2016 during the Cyber Grand Challenge, and it was actually so impactful, and I can't say that it was, it might have been co-evolution of techniques, but the ideas sound to such an extent that almost every single competitor in the DARPA Cyber Grand Challenge actually used a technique identical to Driller. So let's take a look at how this works. Again, we have our program, control flow graph, and our test case corpus slash symbolic constraint corpus. So we start with our familiar input seed. It only triggers 5 basic blocks. We start mutating. Basically, we run a fuzzer. And eventually our fuzzer is unable to make any additional progress. It gets stuck again on this branch. So then we say, oh, the fuzzer is stuck. Let's switch into symbolic execution, but avoid the path explosion by targeting just this branch, right? So we switch into symbolic execution and we create a constraint that can lead code execution into fuzzer was unable to trigger. And then we move back into the fuzzer. So the fuzzer creates a seed based off these constraints, or Driller creates a seed for the fuzzer based off these constraints. The fuzzer keeps running and starts mutating these the seed that Driller found, and eventually, by luck, triggers the correct input to find this bug. Right. So this is a very contrived example to demonstrate a success case of this technique, but in general, the idea with Driller is to use the strength of some techniques to counter the weaknesses of others. So that's all great, but let's take a look in the past and we say, okay, in 1975, we in one of the original papers describing symbolic execution, they said that, hey, we're all very excited about these automatic analysis techniques and so forth, but they're a long way from being able to actually do anything, right? So let's take a look on our CVE graph and see what I think happened to explain the rise in the vulnerabilities found and so forth. So we have 2 increases in vulnerability discovery. One right at the beginning of 2006, and the other one partway through 2015. I think what happened is, in 2006, we legitimately realized that security is an issue. Microsoft started taking security seriously. Other companies started taking security seriously. We started seeing the introduction of various serious security techniques and compilers and so forth. But then in 2015, I think was actually the adoption of human-run cybersecurity automation techniques, such as American Fuzzy Lop, or even some early variants of reasonable symbolic execution techniques and so forth. This period also coincided with the DARPA Cyber Grand Challenge, an event that I mentioned several times. Now I'll go in depth into. The Cyber Grand Challenge was a competition run by the Defense Advanced Research Projects Agency, DARPA. In a previous form, when DARPA was called ARPA, they funded the creation of ARPANET, which turned into the internet. DARPA looks at techniques where a lot of research has been done, but maybe not a lot of engineering, and then they throw in incentives to push these techniques to the finish line. With that, they looked at a lot of these automated analysis techniques, and they said, okay, we have a lot of these automated techniques, but humans are running them. But what if we create something where automation can run automated techniques, and we really create an automated cybersecurity expert? This picture of the stage is the result. There were 7 entrants that made it through the qualifying round, and they were all fully automated hackers. There is this fence over here you might see. This is a government-secured, military-secured air gap to ensure that there's no human interference between the audience. This all took place in a gigantic room I'll show in a sec. This is the gigantic room, but I'll show the view from further back. These computers basically just fought a cyber war against each other for like 8 hours. Their only way for the computers to talk to the outside world, like the Ethernet cable was physically cut and so forth, the only way for them to talk to the outside world was this little robot, where one organizer-run machine would burn DVDs, and this little robot would drop them outside of the air gap, which was crazy. That's how they reported what was going on in the cyber war. Why do this, right? Why this cost an enormous amount of resources. These are all custom racks with water cooling, and they were set up on stage in Las Vegas at DEF CON in 2016 to fight this cyber war in front of thousands of people. Well, I think we all realize that cybersecurity experts are rare. They're like a special kind of flower. And growing a flower is not easy. You have to just make the raw material of a hacker. It takes at least 9 months, and then you have to raise them, and you have to nurture them, and so forth. But instead, if you could create a machine that was equal to a hacker, to this rose, then, of course, you can copy a machine. You can scale a machine much, much more than you can scale a human. And in the end, you could create this task force of machines and humans working together to make security safe. So did this work? Kind of. Right? It worked in the sense that it was a humongous, amazing spectacle. Thousands of people came to watch these machines fight each other on stage. The public event portion took place, I think it took about 3 hours, but all day the teams were over here in this corner on couches rooting for their machines, nervously watching them battle each other back and forth. Of course, I was the captain of one of the teams, Team Shellfish, that had this machine over here. We were a group of students. I was in grad school at the time. A group of kids, basically. Some of our team were high schoolers that were working in the lab at UC Santa Barbara. And we built this crazy machine with, grad student development practices and so forth. To give you an idea of the insanity, at one point, in a practice session, there were a number of practice sessions before the final event, and in a practice session, our database crashed, and the practice sessions were hands-on. You could inspect what your machine was doing and so forth. So when our database crashed, in order to continue the practice session, we created a paper database where we were literally writing down the events that happened and firing off APIs based on these events manually, because our PostgreSQL took a dump. In another scenario, we tried to adopt more grown-up development practices, and we said, okay, we heard this thing called a code freeze. We're going to try to do a code freeze, sometime before the competition, so that we don't make breaking changes right at the end. And so we triggered this code freeze. Said, okay, that's it. Nothing else happens. Boom. And of course, a couple days later, we have commits like this. God, please forgive me for this commit, and various similar things. So the code freeze didn't quite work. In fact, it worked not at all that we spent the entire night right before they cut the cable with a pair of scissors, making final fixes, complete fundamental crazy changes to our system to tweak it right before then. You can see a full video of our a time lapse of this effort on YouTube over there. All right, but at the end of it all, we created the mechanical fish, one of the world's 7 first completely autonomous, what are called cyber reasoning systems, machines that are capable of taking never before seen software, automatically analyzing it, finding vulnerabilities, exploiting those vulnerabilities, and automatically synthesizing patches for these vulnerabilities. We won third place with a prize for third place of $750,000, which is a fortune for a bunch of students running a computer hacking CTF team. This was super awesome. I'll mention there's a number of awesome parts that we can pick apart. This we had the best offensive capabilities in the game. We were tied for the best defensive capabilities. I'll mention one thing in that we are the only cyber reasoning system in the history of humanity to achieve a palindrome score in the competitions. That was really cool. All right. Anyways. In 2016, we really created an infant of a cyber reasoning system. It ran on a very, very simple, or it could analyze a very, very, very simple class of programs. The programs for the Cyber Grand Challenge, in order to make the challenge feasible, were written for a very simplified operating system that supported 7 system calls: read, write, select, memory map, memory unmap, get random, and exit. Their equivalents, right? There was no persistence, no threading, no networking, nothing like that. It was very simple. And the types of vulnerabilities that we supported were very specific. There was, sorry, my mind just went blank. There was, any sort of a pointer override, if you can really overwrite a memory pointer and use it to hijack execution. We did support more complex things like automatic wrap chain generation, but really things had to line up pretty well for this to work. And the automatic repair that we created, our automatic patching of the vulnerabilities, actually didn't care about the vulnerabilities at all. It just applied a bunch of binary hardening techniques, which is a very hard thing to do, but not what you think about when you think about patching a vulnerability. And we also had very limited high-level planning. It was mostly like hard-coded strategies that were being used. And the interesting thing is, think back to that quote from 1975 from the authors of Select, one of the first symbolic execution tools. The use of these tools, they said, is still in its infancy. Well, in 2015, Mikhail Zalewski said something very similar, right? and as you saw, and unfortunately, this is still correct. Still, 5 years later, the use of symbolic execution, concolic execution, static analysis, other emerging technologies to spot substantial vulnerabilities in complex, unstructured, and non-annotated code are still in their infancy. If your code uses 7 system calls, no persistence, threading, networking, etc., we got you covered. But real code in the real world is still a problem. Why is this? Well, this is the difference between theory and practice. Here's what academics think the world looks like. The majority of it is research. And that research has now been, pretty well researched, and we're still pushing forward. But, the engineering and the business part, we feel, okay, it's just some small details that'll happen. And here's what is probably the reality, right? Research is the first step, and then you need to make it work, and then you need to sell it or make it adopted. And this is a not easy thing to do. So let's see what happened when we actually tried to adopt these techniques and so forth into the real world, and when others have tried to do that. This sort of digital business thing, right? We ran into a number of problems. Problem one is language support. The number one thing, and right after the Cyber Grand Challenge, I got a lot of phone calls from a lot of people wanting to either use this technology or adopt this technology or so forth. And the number one problem that we ran into was language support, because the DARPA Cyber Grand Challenge was a competition designed around binary code. All of the machines analyzed binaries. And specifically, they analyzed binaries that were compiled from C, right? That was the best case scenario. But unfortunately, depending on who you ask, if you ask the TO language index, it's very hard to estimate, of course, code quality, but C has somewhere between 3.5% and 17% of market share. And all compiled languages altogether have somewhere between 18% and 30% market share. So already this is pretty limiting. The number one thing that I kept hearing in these phone calls is, here's my Java Enterprise application. Can you find bugs in it? And the answer is no. Our stuff only runs on binary code. So now, we've been slowly developing in still a very academic, researchy sense, Java support. But there's what about Python? What about PHP and other, these top languages? This is a problem. Problem number one. Problem number two is that code doesn't just exist and run. It needs to be deployed, configured, and so forth. And current solutions, such as everything developed for the Cyber Grand Challenge, require a ready-to-run system. Or in the absence of a ready-to-run system, they try their best to analyze things statically and provide huge amounts of false positives, which make it much less useful. There are kind of two variants of this. One is that it's very rare to actually have ready-to-deploy and pre-configured instances of a system ready to go, right? Extremely rare. Most, large companies with complex systems, there's, some development environment that someone took a month to deploy, integration environment that someone took a month to deploy, and a production environment that someone took a month to deploy. If you're auditing the security of this code, you need to take a month to deploy an auditing environment. That's not very fun and also not very effective. Then you'll probably instead just look at things manually. We have no automated techniques right now that can infer and try to automatically deploy these things. That is very much an unsolved problem. And then problem 2B is, even when deployment environments do exist, security flaws can often be introduced through the configuration, or through bad configuration rather than bad code, right? And no one is gonna provide you with insecure configurations because they've probably tested all the configurations that they have on hand. Right, so now we need to have something that can automatically try different configuration. Nothing like this exists. It's another kind of gap from theory to practice that we're missing here. Problem 3 is oftentimes you can't get your hands on the code at all, right? If you're auditing the security of some software of some bank, the bank might not want to give you access to their software, and now you are kind of screwed. Oftentimes, in order to actually do this sort of automated analysis, you need the data too. You need data that these applications will process, and that can be even trickier. Problem 4, interactivity, right? Oftentimes, even if you have the code, even if you have a configuration ready to run, even if you can run it and analyze the specific language it's written in, the target system might have a bizarre configuration. I've actually been asked to look at an autopilot system, right? That it's the worst case. The autopilot system measures real-world parameters and needs them to make sense. It needs air pressure to make sense and so forth. That's a very hard thing to interact with programmatically. Problem number 5 is that even when we can interact, set up, etc., the amount of vulnerabilities, the types of vulnerabilities you can detect are still pretty limited. Right now, mostly, we are very good at detecting memory corruption vulnerabilities, but there's a lot of other vulnerabilities out there that programmatically are undetectable, which is a major issue. Problem 6, people resist. Shockingly, people don't want bugs in their software found all the time, right? There's a now kind of infamous commit by Eric S. Raymond, one of the early leaders of the open source movement, who maintains a library software called Gift2PNG. And he was so tired of getting bug reports with crashes that were with bugs that were found by fuzzers that he created a segfault handler to cleanly exit from the program when it crashed, because then a fuzzer wouldn't be able to, with a default configuration, detect this crash, right? So developers are fighting back against automated analysis because they don't want to deal with all of these bug reports. Academics are starting to get in on the fun as well. There are now techniques to automatically protect a program against automated analysis by injecting decoy bugs or injecting or tweaking the code to induce worst case behavior in fuzzers and other analysis engines. This has, of course, a long history in malware. Malware doesn't want to be analyzed. And I even have today a couple of concrete examples from the Cyber Grand Challenge, right? In the Cyber Grand Challenge, you remember these 7 machines fought each other. And by the way, there are more than 7 machines on stage. Those are the organizer machines that are running the game. There was a lot of visualization. These CDs that were transferred across the air gap were then visualized. And one of the visualizations was this, what was called the intestines view, where it would try to visualize execution of 2 different patches of a program, for example, right? And you can see down here, there's a instruction trace that it's showing. Well, this system was based on QEMU, and one of the things that we inserted into that our cyber reasoning system inserted into every program that it patched were a bunch of attacks against QEMU in case one of our competitors got a hold of our program and tried to analyze it for additional vulnerabilities. During the game, when the organizer machines were analyzing one of our patches, we hung up their machine with a denial of service attack by accident. It is this attack that carried out, that induced some worst case behavior in QEMU and made it soft lock on a floating point square root with specific inputs. Bad news, but this can happen to any cyber reasoning system when analyzing code. All you have to do is put in 4 instructions into your source code, and it becomes unanalyzable by anything using QEMU. Likewise, we had an attack against Symbolic Execution, and it's very intricate, but the basic idea is we would detect if we were being analyzed by Symbolic Execution engine. This is easy to do. You compare the return of a random value against some very hard-coded string. This will almost never be true in real life, but in Symbolic Execution engine, most likely it'll be modeled as an unconstrained return variable, and the Symbolic Execution engine will happily go down this path by adding that constraint. And now you're screwed. You're in this multi-pronged attack, specifically against Symbolic Execution, which will loop continuously, fill the output buffer to exhaust memory in the emulator, allocate tons of memory to exhaust memory more, induce a path explosion with spurious randomized conditionals, and complicate path merging by doing different things on the different paths. This is pretty effective against preventing Symbolic Execution from analyzing your code. Finally, there's one more problem, and that's if everything works beautifully, if we find the bugs, then we still have this problem. Eric S. Raymond got upset, and by the way, he later, very shortly after that, he just got fed up with the whole code base and rewrote it in Go. But he got upset because people just kept overloading him with these bug reports. And it's very annoying. And it's annoying because each bug report represents some human effort that has to be exerted to fix it. I mentioned we do this binary hardening, the general binary hardening. That's not what you need to fix these vulnerabilities. That's just a band-aid, a temporary protection method. What you need is human effort right now with current techniques to fix these vulnerabilities, and that is something that we still don't have. The whole problem is we don't have enough effort to scale. So what are the solutions for this? Well, we're working on it. The research is almost done. Thank you for listening. I hope you're having a great Disclosure Con. If you are interested in asking questions, I'll be on the Q&A session, of course, but you can always contact me on Twitter or over email. If you're interested in visiting the lab, maybe you're in between things in your careers and so forth, we have visiting positions in our lab available, but with COVID it's a little crazy. If you're interested in some of the underlying technology under the techniques I've talked about, check us out on GitHub. Everything that we built for the Cyber Grand Challenge was open sourced. The biggest part of it is the program analysis engine itself called Anger. Thank you for your attention, and I hope to see you in the Q&A.